включилось. А есть ли звук? Есть звук, да? Хорошо. So today we're going to start new chapter, and this is actually the first real chapter on commutative algebra, because if you look at what we've done so far, only a few statements can actually work over commutative rings, but most of the statements and most of the definitions work for even non-commutative settings, like definitions of Artinian rings and Artinian rings. Well, for example, Hilbert basis theorem is something for commutative rings, or generalized Nakayama's lemma is also something for commutative rings, but just a few exceptions. But the localization, so the chapter 5 is the chapter about localizations. So localizations work nicely mostly for commutative rings. There are versions of localizations for non-commutative rings, but they're not so kind of nice and useful. So let's start with the definition. This will be a series of definitions with some elementary properties that I leave you to check as little exercises. So first definition we already know. I just want to remind this: a subset S in some commutative ring R is called multiplicative if we have two properties. So one is in the S, and if we have two elements A and B in the S, then the product is also in the S. So the goal is to use this set as a set of denominators for some fractions. So if you want to multiply fractions or add fractions, you need to know how to multiply denominators, and this is what we kind of add formally in the definition. Okay, so for multiplicative set S, we define a relation. So define a relation on the pairs R cross S. So we think about element R as the numerator and element S as the denominator of some fraction, and we say that two pairs are equivalent if there is element U in the multiplicative set S such that xtu is equal to the y su. So notice that naively, if you want to say that, well, think about this as a kind of fractions R over S, and this is y over t. You want to say that two fractions are actually the same if you have this, but maybe without U, right? That would be a very naive definition. But I claim that this relation is actually an equivalence relation. And if you don't write this U here, you won't be able to prove that this equivalence relation is transitive. So it's essential. I'm going to leave this as an exercise, but it's essential that you have this U in the definition.
RTU equals RTU probably, not X.
Let's see. So yeah. Thank you. I just changed notation, so it was X in my notes. Okay, so that's a definition of an equivalence relation. So part 3 of this definition. So the set of equivalence classes is denoted as inverse R, and this is called localization of the ring R at the multiplicative set S. And the fraction x over S, so is the class of the pair. So part 4. we can define addition and multiplication. So if you have two classes, so let me write x over s and y over t. So you can define addition of such two fractions by very naive formula that you know very well for rational numbers. This is the same thing as tx plus sy over st. So this is where we use that the set S is multiplicative. And of course we can define in the same way products of two fractions. So again, I leave this as a little exercise to check that these two operations are well defined. So these are classes, and the answers, if you change the representative, so you also change the representative here for the answer for the same class. So operations are well defined, and this is exercise.
It's called localization by multiplicative subset or
Localization of the R at the multiplicative set S. And the last part of the definition, more like a standard notation, we have a canonical map that I'm going to denote iota and with the index S for the multiplicative set. And this is a map from the ring to its localization at S. And it just takes element x and sends this element to the fraction x over 1. So it is easy to see just by definition of the localization that if you apply this map iota S to the set S, you will get something which sits inside invertible elements of the localization. Right? So in the localization, every element in the S becomes invertible. Well, that is because if you have element in the S, little s, the inverse is 1 over S. So this is our formal definitions, and here I want to say that I have examples, but kind of again more like a list of another definitions than really examples. So we can take an element in the ring R and you can associate the multiplicative set to this element. This is just the set of all powers of this element. So that's an example of multiplicative set, and this example we already used in the beginning of the course. Now, notation for this localization is the following. You just write R with a subscript f, and this is by definition the localization at this multiplicative set. So take f, associate this set S to this f, and this localization with this specific multiplicative set has this notation. Well, of course, elements here are just nothing but elements of the form x over f to the n. So that's a general element in this ring where x is in the R. So x is in the R, n is some non-negative integer.
F is it's any element.
Any element.
Can the nilpotent can be.
Yes.
Units. Yeah, okay.
For any element, we can see that this set is multiplicatively close, so that's what we need. So, second example, second useful class of multiplicative sets is the following. You can take a prime ideal, and then immediately from the definition of the prime ideal follows that the complement to the prime ideal is a multiplicative set. And the notation for such localization is RP. So for this specific multiplicative set, there is special notation. So of course, fractions here look like x over y, where of course x is in the R, but y is not in the prime ideal P. So that's again a general element in this localization. And the last thing that we already seen on the seminars is the following. You can take a domain and S is just the set of all not zero elements. So for this localization, there are many notations, but I prefer this notation Q of R because this is probably the shortest possible notation, and this is just the localization at this multiplicative set. So for example, if your ring is just a ring of polynomials, then the localization, maybe I just write the Q of polynomials. So the localization is exactly the field of rational functions. So notice, of course, that this Q of R is a field for any domain. So for polynomials, this is a field of rational functions. Of course, you can do this for one variable, you can do this for several variables. That's the same thing, essentially. And the example that we all know very well, if you do this construction with integers, you'll get rationals.
Can it be so that the iota S is not an embedding?
Sure. We will see examples of this. We actually even describe the kernel of this map in some sense. Oh, essentially, this will be a map that is not embedding in the case where you localize at some S that contains zero divisors. Okay, so first theorem about localizations is the following: universal property. So universal property of the localization. So let psi be a ring map between two rings, R and R prime. So then condition that the psi of the S, well, I continue to assume that there is a multiplicative set S inside R. So there is a map of two rings and multiplicative set S. So psi of S is contained in the set of invertible elements of the ring R prime, if and only if there is map rho from the localization to the ring R prime, such that the composition of the rho and iota is exactly psi. So probably it's easier to look at the following commutative square. So you have the canonical localization map, iota S from R to the localization. Now suppose you also have some other map psi. So then this map psi maps every element in the S to the invertible elements if and only if there is another map rho, so such that this triangle is commutative. So moreover, we can say that ring map rho is unique, and we also have some control about of the kernel. So the kernel of the rho is the same thing as the kernel of psi, but then you also need to do the extension of the ideals. Well, remember, in general, when we discussed this situation like this, you have a map between two rings. You take an ideal I here. You can construct an ideal in the R prime. Notation was I R prime. So that was ideal in the R prime generated by all the images of the elements in the I. So this is just a special case of this notation for one specific ring, which is just the localization. Okay, so let's prove this. Well, in one direction this is completely trivial. So suppose first that map rho exists. So then in this case we just used commutativity of the diagram and compute psi on some element S in the multiplicative set S. And I can do this by, well, first I need to apply iota and then I need to apply rho. But if I apply iota, by definition, I will get S over 1. Then I'm applying rho to this S over 1. So I need to understand that this element is invertible. Well, but this is clear since I can take psi of S, multiply this by the rho of 1 over S. Right, so 1 over S is an element here. It makes sense to apply rho to it. And now I just plug in this formula that the rho, so now I just, so I plug in this formula, the first formula into the second formula. So this will be rho of the S over 1 times rho 1 over S. Well, this is a ring map, so this is rho S over 1 times 1 over S. So this is 1. So we see that this psi of S is an invertible element. Okay, so if we know that there is such map rho with this commutative square, then we have this inclusion. Okay. Now let's go in the other direction. So now suppose that the psi of S is contained in the invertible elements of the R prime. I can just by definition set that the rho on some fraction x over S is psi of X times psi of the S and inverse. So this is well defined. Right, if you have X over S is the same as, say, some Y over T, this means that there is element U in the S such that X T U is the same as Y S U. Now just apply map psi to this identity, you will get psi of X, psi of T, psi of U, and this will be psi of Y, psi of S, psi of U. Now we know that psi maps elements in the S to invertible elements, so I can just take the look at this psi of U on both sides and just cancel this. And then I just rearrange the terms and I'll get what I want. I'll get exactly that psi of X, psi of S inverse is equal to the psi of Y, psi of T inverse. So that's a well-defined map, and the rest of the claims here are completely trivial. So you can see that the diagram is commutative, and this ring is definitely a ring homomorphism. And moreover, you can see that such map is unique, because whenever you have such map, it will always be given by this formula. You can think about this, right? For when S is equal to 1, this is clear, more or less by the commutativity of the square. But if S is not equal to 1, well, you just multiply by S and then do the computation. So such map is unique. So the only thing we need to show now is the claim about the kernel. So the kernel of the map rho, well, this is by definition all the fractions x over s such that psi of x times psi of s inverse is equal to 0. Well, but this, if this is the case, well, this is 0, so clearly psi of x is equal to 0, right? Because psi of the s is invertible element. So this sits inside the kernel of the psi, and then we also can multiply this by any element in the localization. Right, so we have this inclusion, and the reverse inclusion is completely clear. So is clear. So that's the end of the proof. So you see that the proof is kind of more or less tautological if you just apply definitions, and all proofs today will be of this kind. So when we just develop some basics of the construction, the proofs are easy. So let's derive a couple of observations from this theorem. So map iota S is an isomorphism if and only if S sits inside the set of invertible elements. This is kind of, again, intuitively completely clear, because if this sits inside the invertible elements, when you invert these elements, it doesn't do anything. It's already invertible. So it means that, well, there's no difference between the ring and the localization of such set. So this has to be an isomorphism. But we also can give a completely formal proof from the universal property. And we consider the following diagram. So there is a map, iota S, to the localization. Now, there is also identity map to the R. So this is identity on the R. And this map satisfies the condition, right? So it maps all the elements in the S to the invertible elements. Just in this case, R prime is equal to R. So by our theorem, there is a map rho here, such that this triangle is commutative. But commutativity of this triangle means that if you take the composition of the rho and iota, you'll get the identity, right? So we see that this map rho that exists by the universal property is the left inverse to the iota. So also we need to show that this is also a right inverse. And to do this, we again use universal property, uniqueness now. So consider map here iota S, again to the localization. And there is another map iota S. Well, clearly the second triangle is also commutative. Well, because they're just the same two maps. So this means that this big triangle is commutative. But if the big triangle is commutative, the map here is unique. So, and what the map that works here kind of immediately, the identity map works here. So it means that this composition is the same as the identity, and this gives us the composition in the other order. So we see. Well, because by the universal property, the map here is unique.
Yes.
And, well, this is just the map to the localization, this is map to the localization. If I take identity here, this is definitely a commutative triangle. So we prove this by the universal property. And there is one more thing that I want to prove by universal property. This is the following observation. So now I have a map. So maybe again I call this map psi. So psi is a map of rings, R to R prime. I have a multiplicative subset in the R, which I'm going to call S, and multiplicative subset as S prime in the ring R prime. So S and S prime are two multiplicative subsets. And assume that psi of S is if you apply psi to the S, you'll get something that sits inside S prime. So then there is a unique map, which I'm going to call psi prime. This is a map psi prime, or maybe I can also call this localization of the map. So S inverse psi. So that's a map. Okay, maybe write it here. So psi prime, which is the same as the localization. And this is a map from the localization of R to the localization at the S prime of the R prime. So there is a map, there is unique map on the localization, making the diagram commutative. So making diagram. So what's the diagram? So in the diagram we have map between rings. We have two canonical maps, iota S and iota S prime to the localization. So this is localization of the first ring, localization of the second ring, and there is an induced map psi prime here. So making diagram commutative. Okay, so moreover, if S prime is exactly the image on the map psi of the set S, and psi is injective, we can assume this is surjective. Yeah. There are two statements here. So if psi is injective or surjective, then the localization of this map is again injective or surjective respectively. So then psi prime is injective or surjective respectively. Okay. Well, first of all, if we know that psi of S is contained in the S prime, so then we can say that the localization at the S prime composed with the map psi of S, well, this is something that sits inside the S prime inverse R, and then I take the invertible elements. Okay, so then I just look at this composition and apply the universal property to this map. Oh, this is the localization. So by the universal property, there is psi prime. Okay, so apply.
I think there should be S prime minus 1 R prime.
Yes, thank you. So apply universal property to the map, so which is the composition of the iota S prime and psi. So that's the map, and I want to apply the universal property. Because of that observation, I can claim that there is, by universal property, there is a map psi prime here. And also I can say that this map psi prime, if I want to compute this on any fraction, just looking at the proof of the universal property, I can claim this is psi of x over psi of s. So not only we can define this map, we can also write a formula for this map, and the formula is kind of what you expected. You just apply this to the fraction, to the numerator and denominator. Okay, now the last part of the statement. So if we assume that S prime is psi of S, so if the map psi is surjective, then the map psi prime is surjective just by looking at this formula. So if psi is surjective, and psi prime is surjective, by this star. So let's call this formula star. Now this surjectivity was easy. Now let's try to prove the last property. So let's take something, so some fraction x over s in the kernel. So this is in the kernel of psi prime. Okay, so if this is in the kernel of the psi prime, well, it means that this fraction is a zero fraction, but by definition, it means that there is some element u prime in the s prime such that u prime psi of x is equal to 0, right? If the fraction is equal to 0, well if you just imagine this equal to, say, 0 over 1, if you just apply the definition when two fractions are equal, it means that there is an element u prime in the multiplicative set such that we have this property. Okay, now we're going to use that this psi is a surjective map on the multiplicative sets. So this means if this u prime is in the s prime, this means that u prime can be written as psi of something. So maybe let's call this psi of u. So then we have the formula that psi of u times psi of x is equal to 0, but this is the same thing as psi of ux is equal to 0. And since we know, well, yeah, we want to show that psi prime is injective, and we know the psi is injective, so we can conclude, so psi is injective, we can conclude that the product ux is equal to 0. But that's actually enough to conclude that the fraction, in this case x over s, is equal to 0. Right? So that's the end of the proof. Okay, so this is the end of the first section about the definition and universal property. Now the next section will look at how ideals behave at the localization, and the goal is to prove the correspondence theorem for the localizations. So we all know that the correspondence theorem for quotients are very useful. So there is a version of the correspondence theorem for localizations, and the goal of this section is to prove this theorem. So next section, 5.2, ideals. In localization. So definition, suppose we have an ideal I in the ring R. So then we can set the so-called localization of this ideal, so S inverse R. Well, you can say that this is just by definition the extension of this ideal to the localization. That's the definition if you want, so that's the definition of this symbol. But you can also look at the definition and you'll see this is exactly the following thing. This is a set of fractions x over s in the localization such that x is in the ideal and s, of course, is in the multiplicative set.
You claim that localization...
Sorry, that's not the ring, so this is the localization. So I will take an ideal and want to define the localization of the ideal. By definition, I take the ideal and extend this ideal to the localization of the ring. And if you look what elements you have in this thing, you get exactly this set of fractions. Okay, so that's the localization of the ideal. The second part of the definition, the saturation of the ideal I with respect to some multiplicative set S is the following thing. So notation is IS. So this is the set of all elements X in the ring R such that XS is an element in the ideal I for some S in the multiplicative set S. So clearly, because we have 1 in the set S, so any element in the ideal will be here. So in general, I is contained in the IS. And it's also easy to see that actually this thing is an ideal. So saturation of some ideal is an ideal that contains the given ideal, and ideal is called saturated, of course, with respect to some multiplicative set S, if ideal is equal to its saturation. We're going to see in a few minutes why this is a useful definition. Essentially, this corresponds to the following situation. You take an ideal, you extend this to the localization, and then you take the full preimage under map iota. So this will be the saturation of the ideal. But you can also give this definition completely formal. Maybe let's do an example. What's the saturation of the zero ideal? So think about this.
All zero divisors. No, the divisors.
No.
Not all the zero divisors. In the pairs of zero divisors that appear to some zero divisors in S. In a sense.
Yeah, I claim that you can describe this as following. This is the kernel of the map. So that's exactly the answer to your question. So the kernel of the iota is exactly the saturation of the zero ideal.
Was the informal definition of the saturation.
It's not an informal definition. It will be a theorem that we prove in several minutes. So you can take an ideal, take localization, that will be ideal on the localization, and then take full preimage under the localization map iota. So this will give you this thing. And another little observation that we're going to use several times is the following. Intersection of the ideal with the multiplicative set S is not empty if and only if the saturation of this ideal is the whole ring. So how to show this?
Well, probably your intersection contains inverted equivalent.
Oh, essentially, what you need to show that the ideal is the ring, you need to show that you have 1 in this ideal. So you need to show somehow that 1 is in the IS. If you just look at the definition.
Yeah.
So then you can take S, which will be at the same time in the ideal and also in the multiplicative set. Then you can take 1 and take product of 1 and S. It satisfies both conditions. It will be in the I, and also S is in the multiplicative set. Okay, now let's prove two propositions. So in the first proposition, so the difference between the following two propositions is where I take the ideal. So in the first proposition, I take ideal J in the localization. So J is an ideal in the localization. So let J be an ideal. So then J prime is defined as the full preimage on the map iota of the ideal J. So that's definitely an ideal in the ring R. This ideal is saturated. And we also have the following. J is equal to the localization of this ideal J prime. Okay, so proof. Let's take an element X in the J prime S, so in the saturation of the J prime. So I want to show that the ideal is saturated, so it would be enough, or one inclusion I always have, so it would be enough to show that if I take such element X, it will be in the J prime. So this is in the saturation. It means that there is element S in the multiplicative set S such that the product of the X and S is in the ideal J prime. Okay. Now, if the element is in the ideal J prime, well, J prime is the full preimage, it means that if I apply map iota sub S, I'll get something in the J. So applying iota sub S to this product, XS, is an element in the given ideal J. But this map, of course, just the same thing as X times S over 1. So then, if I know that XS over 1 is in the ideal J, well, in the ring, in the localization, I can multiply this element by the 1 over S. So then, X over 1, which is the product of the XS, which is over 1, which is element in the J, times element 1 over S, is in J. But from this I can conclude that actually X is in the J prime. So the ideal is saturated. So we proved the first part, right? So now we need to show that this equality is also true. Now maybe I need to finish this. So J prime is saturated. Now for the second result in this proposition, take a fraction X over S in the ideal J. So then again, I do the same thing. This is in the ideal J. J is in the localization. I can multiply this by the S, well, by the fraction, say, S over 1. And then I can conclude that X over 1 is in the J. But this means that X is in the J prime. So, and this means that X over S is in the J prime times the localization of the ring. So this gives us inclusion in one direction. Now we need to do inclusion in the other direction. So conversely, if X is an element in the J prime, so then X over 1 is an element in the J. But if X over 1 is element in the J, I can immediately see that the J prime times the localization of the ring is contained in the J. Well, just because I know that the J is an ideal. And that's the end of the proof. So in the next proposition, I start with an ideal I in the ring R. So this is an ideal. So then, again, I have two observations. The localization of this ideal is the same as the localization of the saturation of this ideal.
We use J first. So ideal J contained in R.
No, this is different situation. So in the proposition here, I have ideal J in the localization. And I want to conclude some properties, for example, that the full preimage is desaturated, but now I have ideal I in the ring. So that's why I want to use different notation. So J is sitting in the localization, I is sitting in the ring. And I have two observations about the ideal. First of all, if I localize ideal or I localize the saturation, the answer is the same. It would be the same ideal in the localization. And the second observation is that what I promised in the beginning, actually, if you take the preimage of the extension, or you can say preimage of the localization of this ideal, you get exactly the saturation of the ideal you started with, ideal I in the ring. The proof is again kind of computation with elements. So if you take x in the saturation, so in the IS, so there is element S in the multiplicative set S, such that the product XS is in the ideal I. Okay, if the product is in the ideal I can again say the following: the fraction x over 1, which is the same as the xs over 1 times 1 over s. Well, this is in the localization of the ideal. So let me write this maybe as I s inverse R. Okay, so what we proved, we started an element in the localization and see that the corresponding fraction, no, we started the element in the saturation and I see the corresponding fraction is in the localization of the ideal. So I claim that from this it is immediately clear that IS times the localization of the ring, so extension of the saturation to the localization, is contained in the I, again, extension of the ideal I to the localization. Right? So this follows from the previous computation. Now, from this thing you can derive two observations. So first observation is that IS S inverse R is equal to the I S inverse R. Well, this is because we proved the inclusion in one direction by some computation. Inclusion in the other direction is completely trivial, because I is contained in the IS, and these inclusions are preserved by the extensions. So we have this. And the second observation that we can also derive from this line is that IS, IS is contained inside the iota inverse of the ISS inverse R. This is always the case for any ideal and any extension of the ideal. If you extend and then pull back, you'll get something that definitely contains the original ideal. Now, if you apply the iota inverse of S to the right hand side of this identity, then you'll get just what you get. So iota inverse S of the, now let me maybe just use short annotation, localization of this ideal. So this kind of in the direction of the proof of the second formula. We already proved this part. Now we need to prove this, and we already proved inclusion in one direction. So what's left is to show that there's inclusion in the other direction. So if I take element in the iota inverse of the S inverse R, then the fraction x over 1 yes, thank you. So then this means that if you apply iota to this x, and applying iota to this x is exactly x over 1, so this is in the localization of the ideal S inverse I. So this means that this fraction x over 1 is equal to another fraction y maybe over s, such that I know that y is in the ideal I and s is in the multiplicative set S. So all elements in the localization, we know that they have this form. So in particular x over 1 has this form. Now we just use the property that the two fractions are the same. It means that, well, there is element t now in the multiplicative set S, such that x s t is equal to the y t. Okay, but the y t is in the ideal y. Y is in y. So, and this is a product of x and some element in the multiplicative set. So this means that the element x is in the saturation. That's the end of the proof. So I think the proofs are a little bit annoying. It's just computation with elements and kind of more set theoretical properties. But maybe you can, if it wasn't clear immediately, maybe you can go back later and watch the video of the lecture again. So,
Localization lives on the saturated. Localization takes on the saturated ideals from
well, the localization is kind of operation that maps sends ideal to the ideal in a different ring. But if you do this extension and restriction, then you get a saturated ideal, the saturation of the original ideal. So about bijection, you're completely right, and that's exactly what I want to derive from these two propositions. So this is the version of the correspondence theorem. This correspondence theorem tells us the following: that there is an inclusion preserving bijection between saturated ideals yes, so the ring is fixed, the set is fixed, and then there is a bijection between saturated ideals of the ring R and ideals of S inverse R. So in some sense we have a description of the ideals and localization in terms of the ideals of the original ring. It's like for quotients, right? We have a description for the ideals of the quotients, like ideals in the original ring containing the ideal with respect to which we take quotient.
ideals such that there is an intermediate ideal between I and IS.
Yeah, that's possible. Yeah. Yeah, so next I want to switch to the properties of the prime ideals. So let P be a prime ideal. So that for shortness I just write element in the spec of R, such that the intersection of this prime and this multiplicative set is empty. So then P is saturated and the localization of P is again prime. So if you take an element X in the saturation of a prime ideal, it means that there is S in the multiplicative set S, such that the product of the P and S is in the product of the X and S is in the ideal P. Now P is prime, right? We have product of two elements in the prime ideal, and we definitely know that S is not in P by our assumption. So X is in P. So any prime ideal with this property is saturated. And we're actually only interested in the prime ideals satisfying these properties. There's not kind of some additional technical assumption, because if you don't satisfy this assumption, well, it means that the localization is just the ring. So it's not very interesting from point of view of the ideals in the localization. Okay, so saturation of a prime is prime, and what we need to show next, we need to show that the localization of a prime is also prime. Okay, so take two elements, two fractions, x over s and y over t. So the product is in the localization of the prime ideal P. So then you have the following. You have fraction x over y, xy over 1 which is the same thing as st over 1 times the xy over st. Well, this is again in the localization of the ideal P. So then xy belongs to the pre-image of on the map iota. Well, sometimes when you, oh, maybe no, that's not what I want to say, no. So pre-image of the iota inverse of the localization of the SOS inverse of the P. So we know that this thing is exactly the localization, sorry, the saturation of the prime ideal P, and the prime ideal P is saturated, so this is in the P. Okay, but if this is the case, x is in the P or y is in the P, and if that is true, then this fraction is in this localization, or this second fraction is in the localization. Okay, so next proposition. So if P is a prime ideal, so in the spec of R, so then the localization Rp is the local ring with maximal ideal, which is just the extension of this prime ideal P. So we can get ourselves a lot of examples of local rings. So that's why local rings are actually important, because many properties of commutative rings you can study by localizations, and when you localize at the prime ideal, you get a local ring necessarily. So that's one of the reasons why local rings are so important in commutative algebra. So proof. And for the proof, I do the following. I take an ideal I in the localization at the prime ideal P. So then, if I take the full pre-image under the map iota of this ideal, and if I take the intersection with the complement to the prime ideal, I'll get empty set. Notice that when I localize at the prime ideal, I use notation iota with subscript just this prime ideal P, not the set S. So I'm going to use several seconds to erase the blackboard. You can think about why this is true.
Proof here on the left. How did we prove that S minus 1p is prime?
So this part, right?
Yes.
So I take two elements in the localization. So I want to show that if the product is in the ideal, one of these two elements has to be in the ideal. So then I do this computation. So by taking this product, which is this part, and multiplying this on this fraction st over 1. Well, since this is ideal, this is in the ideal, this is an element in the ring, this is in the ideal. Now, if this is in the ideal, it means that under the map iota, well, this thing is exactly the iota applied to the element xy. So I can claim that the xy is the preimage of the under map iota, well, of some element in the localization of the prime ideal. But now I know by second proposition that I proved that this thing is exactly the same thing as saturation, and I already know that any prime ideal is saturated. So this is P. So then I have that the product of x and y is in the prime ideal. So I can conclude that x is in the prime ideal or y is in the prime ideal. But that's enough. For example, if x is in the prime ideal, then this fraction will be here. Yeah, so how about this intersection? So why this intersection is empty?
Well, because if it wasn't
Mm-hmm.
empty, there was, in I was 1.
Yeah, so otherwise, if this is not empty exactly by that small observation that we've done in the beginning of the lecture, then the saturation will be just exactly the localization of this ring. And, well, we won't consider proper ideals, so not equal to the ring. Okay, so but if this intersection is empty, equivalently, I can say that iota inverse P of the ideal I is completely contained in the prime ideal. Right? Just going to the complements. So if this is completely contained in the prime ideal, well, this means that ideal I is contained in the extension. Well, this is the same thing. You look at these two ideals, right? You do the extension. You extend left-hand side. You extend the right-hand side. Well, if this you have such an inclusion, you have the inclusion for the extensions, and I is definitely contained in this thing and then extended again. So we see that if you start with any ideal, this is necessarily contained in this ideal. So there is only one maximal ideal. Or for example, take I to be any other maximal ideal. It has to be inside this maximal ideal, so they coincide. So there are no other maximal ideals. Okay. So probably I want to finish the lecture with some examples. So examples. In the first example, let's take a prime integer. So then we can describe the localization. So if I localize at the corresponding prime ideal, what's this other ring? So I can think about this as that all fractions m over n. So this is just a rational number, such that so P does not divide n. Okay?
So what's that like?
Hmm?
So is it periodic numbers?
No. Periodic numbers is a completely different construction. It's a completion. This is just localization. So let's discuss a couple of questions. Can you describe the spec of this thing? The spec and then the crude dimension.
Well, as we said, the only map
Yeah, there is a unique so that's a local ring. So there is a unique maximal ideal. So we can also describe this unique maximal ideal. So in this case, P z localized at P looks as follows. So this will be again fractions m over n. Now, what conditions we have? Well, we need to say that M, okay, P divides M, right? But P doesn't divide N. I think this is two conditions that we need.
Any other ideal prime, any prime ideal here must be an image of the localization of prime ideal in Z, right?
Yes.
And every prime ideal in Z has an element intersection with the complement P with D, therefore there are no other prime ideals in this localization other than the localization of the ideal generated by Z.
So this ideal,
Yeah, it's the only element of the spectrum.
how about 0?
Well, except for 0.
Yes, so we have only two ideals, 0 and this ideal. So the crude dimension is 1.
Yeah.
So that actually answered to a question you asked last time, an example of a ring with finitely many prime ideals, which is not Artinian. So we have only two prime ideals, but the dimension is 1, not 0. So that's a counterexample. Okay. So another example, well, we can do the following. We can take maybe a very specific ideal P, which is just generated by the x minus a. This is in the polynomials in one variable, so a is just an element in the field.
This is a prime ideal P generated by x minus.
Yeah, so this is a prime ideal generated by the linear polynomial x minus a. So it's actually maximal ideal. What would be the localization of the polynomial ring at this prime ideal? Now again, we can describe this, well, everything sits inside rational functions, so we can describe this as a rational function, say f over g. So the description is kind of similar to what we already have done for integers and rationals, so that's a rational function with the property that, so what we need to say, we yeah, so that's the condition that I want. G of a is not 0, yes. And we also can describe the corresponding maximal ideal. Again, all such fractions, and condition that the G of a is not equal to 0 is still here. But what would be another condition for the f? Yes. Okay, it looks like I still have several minutes. Maybe I start next section, because in the beginning of the next section I have a couple of boring definitions. So next section, localization.
What is geometrically the localization in such a deal?
Well, I wanted to discuss this on the seminars, but you can describe the spec of the localization. You have a map from the ring to the localization, for example, the prime ideal. So it means that you have a map from the spec in the other direction, and the image of this map, if you consider spec of the RP mapped to the spec of R, this is exactly the intersection of all open subsets containing point P.
Ah, that makes a lot of sense, yeah.
So localization of modules. So again, I start with some definition, completely trivial and just a repetition of what we already know. So S is a multiplicative set. Now we have a module, so M is an R module. And again, we can consider pairs M and S. We can introduce the equivalence relation in the same way as before. So two pairs are equivalent if there is element U in the multiplicative set S such that UTM is equal to the USN So again, we think about this as a fractions. This thing is an equivalence relation. So let's say first part. The second part, the set of equivalence classes in this case is denoted as inverse M, and M over S is notation for the class of such pairs. Now we can also define operations, but in this case two operations would be addition of the elements in the module. So if I have one fraction M over S and another fraction N over T, then I can define the sum as Tm plus Sn over St. Again, little exercise to check that this is well defined. But this only gives us a structure of an abelian group. We also have a structure of a module by observing that you can multiply fraction in the localization of the ring and the fraction in the localization of the module in the most naive sense. This will be just xm over st. So here, this is in the S inverse R, this is S inverse M. So naturally, localization is a module of the localization of the ring. Of course, it will be a module over ring itself, because you can consider fractions where S is equal to 1.
Is it like some sort of extension?
Extension of what?
Scalars?
Yes. We will see this actually extension of scalars. We're going to see that the localization is actually tensor product with the localization of the ring. But this is not how this is defined. It's what I said is a theorem. Okay. And finally, the last part of this thing is that there is again a canonical map. I'm going to use this. So there is a canonical. Yeah, so I'm going to use again notation S. Maybe it's not the perfect notation, but this will be a map from the module to the localization of the module, and it sends element in the module to the fraction M over 1. Okay, so a couple of remarks. So first of all, localization of ideals is a special case of localization of modules. If you treat any ideal as a module and you apply the construction of localization of modules, you get exactly the same answer. And the second remark is that if
And then it's called localization of module as
at the multiplicative set S. And if in the special cases, if multiplicative set is just set generated by one element, so powers of one element, then in this case the notation that we're going to use is iota sub f from the module to the localization. So the special structure of this multiplicative set is reflected in the name of this localization map iota. And if S is just the complement to the prime ideal, again, notation is iota sub p from the M to the MP. So in this case, we have two special notations, one for localization. We write this P for index P for localization, and also the same index P for the map iota. I think I should have said this when I defined this for rings, not just for modules. But for rings, it will be a special case.
So we don't define localization of module if S is just 1f squared. Well, in rings we define it like Rf. Shouldn't we write this Mf?
Maybe. I'm not. Yeah, I think maybe we can use this notation. So, yeah. So let's use this. Yes. So the point is that for the special examples of multiplicative sets, you have special notation for the localized objects and also for the localization maps. Okay, it looks like I still maybe have time to prove a proposition. So the kernel of the map iota S is exactly the set of all elements in the module M such that annihilator of this element M intersection with the multiplicative set S is actually empty. So this is first part of the proposition. Second part, so if annihilator of the module M intersect with S is not empty, then the localization of this module is just zero module. And 3, if M is finite and the localization of the module is trivial, then the annihilator of M intersect with S is non-empty. So you can see that for finite modules you have if and only if condition when the localization is zero. Okay, for the first part, if I have element M in the kernel of the localization map, so this is equivalent to saying that the fraction M over 1 is 0 in the localization of the module, which is equivalent to say that there is element, say T, in the S, such that the product of the T and M is equal to 0. But that's exactly the claim that we have in the proposition. We have element which annihilates element M and at the same time is in the set S. Okay. Second part. So if we take some T which is in the annihilator of the module M and also in the multiplicative set S. So then
So there should be like not empty. Annihilator M intersect with S, not empty.
yes, it is not empty condition, yes.
And in the third also not empty.
In the third, not empty, but it's okay. So we need to show in the second property that if we have something in the annihilator and which is also in the multiplicative set, then any element is actually zero element. So let's take something which is not zero, of course, which is in the intersection of the annihilator and the multiplicative set. Now, if I take any fraction, say M over S, I can present this as Tm over Ts. But Tm is 0. T is in the annihilator. So any fraction is equal to the zero fraction. So 3. So now we know that the module is finite. So let me write this as a sum Rmi. So this is just names for finitely many generators. So that's a finite sum, maybe n generators mi. So then if I look at the localization of this module, I can generate this module essentially with the same generators. So I can write that this is S inverse R, but now I need to write mi over 1. And I know that the localization is 0, so if every generator is 0, it means that, so this is for any I, it means that there is element Ti in the multiplicative set such that Ti mi is equal to 0. And then I can take the product of all such ti's, and this will annihilate any generator, so it annihilates any element in the module. So this is in the annihilator of the module, and also this is a product of elements in the S. So this is in the intersection with S, and that's what we need to show. Okay, so this is the end of today's lecture.
Why is product of ti is not 0? Yeah, but it's still.
No, in general, it's possible to have 0 divisors and multiplicative sets.
Yeah. So I think we should say that R is the main, then geometry.
But is this really a problem in the proposition? If this is a 0, I only want non-empty intersection.
Yeah, okay, I understand.
So there is no problem.